Okay, so let's go ahead and cover chapter 5, concepts only for Newton's laws of motion. So the big ideas here are that a force is a push or a pull. Any object at rest will stay at rest if the net force acting on it is zero. A net force will cause an object to accelerate, and all forces will come in equal but opposite pairs. So, first of all, a force can be a push or a pull. A force is a vector, it has magnitude, and it also has direction. Mass is just the measure of how difficult it is to change an object's velocity. Or you can also think about it as the quantity of matter or how much matter an object contains. And I've provided a table that includes several common masses that you might have to use to work problems, though I will probably give you this information were you to need it. So let's just jump right in. Newton's first law. And I know you've probably heard of these, but we're going to go over them in a little more detail today. So here's our question. If you stop pushing an object, does that object stop moving? Only if there is friction. If we have no net external force, that object is just going to keep moving at a constant speed in a direct line, or it's going to remain at rest. And this is known as the law of inertia. So Newton's first law is also called the law of inertia. And it is officially stated as an object at rest remains at rest as long as no net force acts on it. And an object that is moving with constant velocity will continue to move with the same speed and in the same direction as long as no net force acts on it. So make sure you commit that to memory. The concept portion of this. So in order to change the velocity of an object, we must have a net force acting on it. Now, an inertial reference frame is important. Proper frames of reference are important because here they must also obey the first law. So your reference frame has to obey the first law too. So somebody who's in a train watching an ice cube will see that ice cube as being at rest. Yet someone outside the train would see the ice cube as moving with a constant velocity. Well, both of those things obey the first law, being at rest and having a constant velocity. Now, imagine if the train were accelerating. Then the person inside the train would still see that object as being still, but the person outside the train would now notice that that object was accelerating. These are not consistent with the first law. Only one of them is. So that would be a non-inertial reference frame. If we have two equal weights, they are going to exert double the force of one weight. And we can actually use this to calibrate a spring. And I wish we could do this in a lab. Maybe we'll get the opportunity to when we are supposed to go back in October. So with that calibrated spring, we can actually do more experiments to discover that acceleration and force are proportional. And you likely already know this. If we have a constant mass and we double the force, we are going to double that acceleration. On the other hand, acceleration is going to be inversely proportional to mass. If we double the mass but keep a constant force, we will actually cut that acceleration in half. So something that is a lot more massive can't accelerate as quickly, and that makes sense. Mathematically, Newton's second law looks like this, and you're definitely going to be more familiar with that bottom one, F equals ma, but we can rearrange it to have A equals F over m. And here are your common units. So for mass, we're going to want to use kilograms mostly. Acceleration will be meters per second squared, and force is going to be in newtons. Okay, now an object doesn't have to have just one force acting on it. It can have multiple forces acting on it. And in fact, an object usually does have multiple forces acting on it. And if that's the case, we're going to have to add all of those forces together individually. So we might have to add the masses together, we might have to add the accelerations together, but we'll have to take a sum of all of the forces in order to determine the net force. And here we just have some typical forces, and these are all in newtons. You can refer back to this if you were to need any of this information. But again, I will try to give you any information that you need. Now, free body diagrams are going to be incredibly important when we start working problems in this chapter. And a free body diagram just allows us to, it allows us to diagram the forces acting on an object. So we see this guy here is pushing on a chair, and this chair is currently on the ground. So if I wanted to draw the free body diagram, I would do so like this. I would draw his force, which is acting on it. And we know that the chair has a weight, and that would be pushing down on the floor. But the floor would be pushing back up on the chair as well. And you will be drawing these frequently in order to help you solve problems. So to draw a free body diagram, you're going to go ahead and sketch the forces. And after you sketch the forces, you're going to isolate that object of interest. Because, for example, in the previous slide, we only care about the chair. So you want to ensure that any forces you're drawing are only acting on that object of interest. Then you're going to choose a convenient coordinate system. And for the previous problem, I would have had the y direction going like this and the x direction going like this. That makes sense. It's convenient. Then you're going to break the forces into their individual components. And lastly, you'll apply Newton's second law to each coordinate direction. Okay, so let's actually try that. If we have a book that's resting on someone's hand, how would the free body diagram look? Go ahead and pause this. Okay, so if we wanted to draw those, we have the hand that is exerting a force on the book and the book exerting a force on the hand. So it would look like this. The weight of the book is the force going down, and the force coming from my hand we'll just label as F, or the hand. You might have noticed that forces always come in pairs, and they act on different objects. So object 1 will exert a force on object 2, and vice versa. Object 2 exerts a force on object 1, and we call these action-reaction pairs. Well, that's the third law of motion. For every force that acts on an object, there's a reaction force acting on a different object, which is equal in magnitude and opposite in direction. Okay, so here are some action-reaction pairs. We see the car on the ground, and the ground has an equal but opposite force on the car. You see the same for a shuttle orbiting Earth. A person touching or moving an object. And yeah, the same here, a person moving an object. So you see the force is equal but opposite in each of these cases. Contact forces are a little bit different. So the force that's exerted on one box, so either 1 or 2, it doesn't matter, will be different depending on the one you're pushing on. So it's going to be different if we're over pushing on box 2 versus pushing on box 1. So how will they be different? Well, even though the forces are the same, those accelerations aren't going to be the same unless the objects have identical masses. And it's possible that these two boxes have identical masses, but we don't have enough information to determine that. So this is something to make note of, that when two objects are in contact, the accelerations aren't going to be the same unless the objects have the same mass. We have forces in 2 dimensions as well. So that means if we have a force that is going in a diagonal direction, so not along the x-axis and not along the y-axis, then we're going to have to split it into its components. The force for the x component and the force for the y component. To do this, we're often going to need weight. And weight is just the mass of an object multiplied by the gravitational force exerted on it by Earth. So that's how we define weight here on Earth. And it is going to be given in newtons. Weight is a force. Now, apparent weight is slightly different, and you've all experienced this in an elevator, on a trampoline. So your perception of weight is based on the contact forces between your body and your surroundings. So if your surroundings are actually accelerating, whether that be in the positive or negative direction, you will feel like you weigh more or less than you actually do. And we'll work problems with all of these. These are just concepts right now. Normal forces are the forces exerted by a surface on an object. So not two objects in contact, but the surface. It's the force that the surface exerts on an object. You see the table is exerting the normal force on the can, on this cooler, whatever that is. Oh, that's the cooler as well. So the normal force is always pointing up. Well, in these cases, because our surface is right here and the object is sitting on top of the surface. The normal force can be equal to, greater than, or less than the weight. So this will just depend on whatever the object is that is sitting on the surface. And one of the last things, the normal force will always, always, always be perpendicular to the surface. So if our surface is slanted like this, then we're going to have the normal force going perpendicular to the surface. So it may not always be vertical. It's perpendicular to the surface. Okay, that is it for the concepts. So here is just a quick review. The force is a push or a pull. An object will stay at rest if the net force acting on it is zero. A net force will cause an object to accelerate, and all forces come in equal but opposite pairs. Thank y'all for watching, and our next video will be over working problems using Newton's laws. Thank you.